Let's take a look at another example here. So in example 3.2.1, we have a single drum hoist. So in this example here, we have a figure that shows us a motor supplying a torque T to a drum that has a radius R and inertia I about its axis of rotation. The rotating drum lifts a mass by means of a cable that wraps around the drum. So here we have our diagram here. We have our axis right here. We have this drum right here rotating, lifting this mass up like this. We can see we have our torque going in this direction, our omega going in the same counterclockwise direction. Here's our radius R of the drum. Has our inertia right here. Here's our mass with a velocity v going up in this direction, acceleration due to gravity going down here. We draw it out in a 2D view for our free body diagram over here, slightly simplified as well. See our torque going counterclockwise with our omega term. Force here, or the tension in the cable itself. Our mass m here, velocity up, weight force going down here. So they also tell us that the drum speed is given to us by omega. Discounting the mass of the cable, so there's an assumption there. We're assuming a massless cable. We're using the values that they tell us now. Our m is equal to 40 kilograms. There's our m right here, 40 kilograms. Our radius r of the drum here is given by 0.2 meters. And our inertia over here, I, is given to us as 0.8 kilograms per meter squared. And they want us to find our acceleration, or our v dot term, if our torque T is given by 300 newtons times meters. So before we start a solution, one thing we want to take a look at is our units here. We can see we're dealing with meters, kilograms, newtons, so we know what we should keep everything, see if any conversions we need to make as we're solving along the way, and we can calculate what we need for our units for our acceleration for our v dot, meters per second squared at the end. So now that we've had that opportunity to read through our problem statement, the next thing we want to do is create our setup page. So on our setup page, we want all the given information clearly labeled. What are the variable names? What are the values? What units are we in? How do they relate to our problem? Simplified diagrams, what they're asking us to solve for, any assumptions we're going to make. So that's exactly what we do here. For example, 3.2.1 for our single drum hoist. All of our given information taken from that problem statement, clearly written out and labeled here, our variables, T, M, R, I, F, and omega, and our values for each of those, units, how they relate to our problem. So T is given to us as 300 Newton meters, which is our torque. M is 40 kilograms, our mass. R is our radius of 0.2 meters. I is our inertia of 0.8 kilograms times meters squared. F is the tension in the cable. And omega is our drum speed. So we redraw our diagram over here, our drum right there, our cable with the tension in it there, our F pulling this mass up with the velocity in this direction, gravity and the weight acting downwards, our torque and our omega going counterclockwise, the radius of our drum there, and our inertia. So what are they asking us to solve for? We need to solve for our acceleration, or our v dot. Assumptions we're going to make is that the drum rotation axis is fixed. So that's going to help us in our solution and what governing equations we choose. So now that we have our setup page completed, we can reference back to all the given information, what they're asking us to solve for, any diagrams. The next step is to begin our solution. The first step in our solution here is to choose a key governing equation we're going to use for solving this problem here. So the governing equation that we're going to use comes from equation 3.2.1 on page 135 of the 4th edition of our textbook here in section 3.2. So we have our moment equation here. Our moment about O is equal to our IO omega dot, where our IO is our mass moment of inertia about 0.0. Our omega dot is our angular velocity of the mass about an axis, 3.0, and MO is our moments about 0.0. So we have our governing equation, general form, right there with all the variables spelled out for what they are for our particular problem here. So now we can use this and easily plug back into that. The next step in our solution is to come up with a free body diagram. So they've given us in the problem statement already the diagram that we can use for a free body diagram here, and they tell us now that we also know our tension is equal to 300 Newton meters, and what we want to do is take a look at this diagram here and come up with our summation of moments about 0.0. So 0.0 is the center of this rotating drum up here, Again, we have our torque and omega going counterclockwise around it. We have our tension force down here, our mass down here. So recall our general equation here for our moment. Have this up here, so moments about O. What are the moments about O? Well, we have the torque coming around here about point O, and we have this force here, our tension force times this radius to point O right there. So you can plug those in, summation moments about O. We have 300 Newton meters from our torque right here, minus our F, our tension in our cable, times the radius distance here of 0.2. We do our right-hand rule here. Tension's positive for our right-hand rule, that's why it's positive 300. This is going clockwise, which is negative with our right-hand rule here, so we have our negative sign right there. So from our free body diagram, we're able to come up with summation of moments about our point O. So for the next step of our solution, what we want to do is plug back in our values into that governing equation. So I rewrite our governing equation in general form here. I0 times omega dot is equal to our MO. So we have our inertia about 0.0, our angular velocity, and our moments about O here in their governing equation. We plug back in. Now we've just solved for our moments about O from our free body diagram. We got this relationship here of 300 minus 0.2 F, where F is the tension in our cable. In our problem statement, we're given our inertia here about 0.0 of 0.8 kilograms per meter squared. So we can plug that in there, and we can plug this in here. From that, we now get what we're going to call equation 1. So this is something to note. As we're going through some of these more complex problems, we're going to have multiple equations that we either need to solve simultaneously, plug one in terms of another. It's great to reference back and give these a name or a number so we can say, okay, we're plugging equation 2 into equation 1, or combining equations 3 and 4 gives us equation 5. So I've started a labeling system here where this is my first equation within my solution here, where I plugged my known values back into our governing equation. We get now 0.8 omega dot is equal to 300 minus 0.2 F. Now the thing I note about this is I have two unknowns in one equation. Don't know my omega dot and I don't know my F, so we need some other relationship to relate these two together, or relate them to another variable that we can solve for. So take a look here. Okay, I don't need that. I need something now involving our F here. So what I can do now is I can go back to my free body diagram here, do my summation of forces, Newton's second law here, come up with equations of motions based off my free body diagram here. So that's exactly what I do. F equals ma, Newton's second law. Let's deal with one direction at a time. I have my chosen coordinate system. I'm going to consider y positive up, x positive to the right. I'm just going to deal with my y direction right now. So I'm going to take the summation of forces in my y direction. Summation of forces in the y direction, I take a look at my free body diagram. Well, I've got this force F coming up here. I've got my weight force coming down here off my mass now, which is mg, and this is equal to the right-hand side of the equation, mass times acceleration, which would be the first derivative of my velocity term over here. So now I have my equations of motion. What are my known values here? Well, I know that my mass is given to me as 40 kilograms. I know now my acceleration due to gravity is 9.81 meters per second squared. And I can go ahead and create a new relationship here based off of that. So my MA, the right-hand side of Newton's second law, is my mass of 40 kilograms. My acceleration is the first derivative, time derivative of my velocity term here, is equal to the summation of forces in my y direction, where I have my F positive going up according to my coordinate system, my weight force going negative according to my chosen coordinate system here. So there's my negative sign there. Weight is mass times acceleration due to gravity. So weight is 40 kilograms, acceleration due to gravity, 9.81 meters per second squared. Plug that in, and now I have a new equation here I'm going to call equation 2, based off of my free body diagram for summation of forces in my y direction. Now from this here, we realized the whole purpose of this was to get a expression for F to plug back into our equation 1 up here, so I can rearrange equation 2 and solve it for F. So F is equal to 40 times 9.81 plus 40 times my v squared there. Simplify this down, pull out that 40 there, and I realize that my F is equal to 40 times 9.81 plus my v dot there. So now I do have an expression for F that I could plug back into equation 1. So as I mentioned, this is where it gets kind of nice to have a labeling system for all of our equations along the way, so we can tell everybody what we're doing. It's easy for someone to follow along with your work, whether it's yourself in the future, the company you're working for, or in this case here, the grader as they're looking through your solution, your methods. So what we're saying here is now we're going to plug this F relationship we just solved for from equation 2 back into our equation 1. That's right here. I rewrite out, okay, here's my equation 1 right here. 0.8 omega dot is equal to 300 minus 0.2 F, where F we just solved for in equation 2, so we can plug that relationship there for F back up into equation 1 right there. I do that and I end up with this expression here, 0.8 omega dot is equal to 300 minus 0.2 times 40 times our 9.81 plus our V dot there. Rearrange, simplify this down a little bit. We end up with 0.8 omega dot is equal to 300 minus 8 times 9.8 minus 8 times V dot. And I'm going to call this relationship our equation 3. So from this here, we remember we want to solve for V dot as our final solution to this problem here. So what we can do is we can rearrange this, solve for our V dot there, our acceleration. When we look at this here and say, okay, I have an unknown of omega dot and an unknown of V dot. We're solving for V dot where we have one equation and two unknowns again in this situation here. So now we need a relationship between our omega dot and our V dot. So we can call our relationship here between velocity and omega. V is equal to r omega here. In our case here, we know the r value, so V is equal to 0.2 omega, or derivative of that, V dot is equal to 0.2 omega dot. So with that relationship there, now we have a factor that ties in our omega dot and our V dot in equation 3. So we can go back now, plug back in to our equation 3 here. So we have our equation 3, I rewrite it out in general terms, 0.8 omega dot is equal to 300 minus 8 times 9.8 minus our 8 V dot there, where now we have this expression here that V dot is equal to 0.2 omega, or rearrange that, solve for our omega dot. So omega dot is equal to V dot over 0.2. So now I can plug in for omega dot with my V dot, eliminating my omega dot from this equation here, because what we're solving for is our acceleration, our V dot. Plug that in there, omega dot becomes V dot over 0.2, which is equal to 300 times 0.8 times 9.81 minus 8 times V dot. I look at this here, one equation, one unknown. That makes us happy. We can solve for that there. Rearrange and simplify a little bit. Multiply this through here. We end up with 4 V dot is equal to 300 minus 8 times 9.8 minus 8 times V dot there. We can add a plus 8 V dot to both sides of this equation to move this over. So V dot is all on one side of the equation. What we end up with there is now we have 12 V dot is equal to 300 minus 8 times 9.81. Do out the math there. V dot is equal to 300 minus 78.48 over 12, which then becomes that our V dot is equal to 18.46 in units of meter per second squared. And again, keep track of your units, do a unit analysis. You make sure that in the end you've plugged in the right things for all the variables for their units along the way. And it's a great double check for your final solution. In this case here, it does check out. That's what we're looking for units. So this is our final answer here for our acceleration.